So what I wanted to start out because we have a solar power demonstration to begin with. And what I have here are two different prisms, and they're both, is anybody a triangle expert? Do you know what kind of triangle that is?
Isosceles,
It's even better than isosceles.
equilateral.
Yeah, these are equilateral triangles. So they're also, if they're equilateral, what are they also? Is Emma here?
What did he?
Miss Heather, is Emma here?
Yeah, she actually said
She did.
equilateral triangle from behind the computer.
Very good. And what? Oh, 60 degrees. Thank you, Zanzin. Yeah, they're equiangular too. If they're equilateral, they're equiangular. And then I'm putting them just down. And what I want to do, this part here that I have my finger on is the reflection off the top surface. So that's the sun kind of glancing off that top surface. And so since both triangles have the same angles, if we put them so that this part here that I can erase, if that's the same on both, that means they're both the same angle of incidence. So the sunlight is coming in at the same angle. So what we can see is that this glass one here is, well, this is actually a larger deflection because the sunlight is coming down here and then this spectrum is up here. So what we want to do is notice this. Here the spectrum is coming down, 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 and then back up. And what I'm doing, I'm turning the prism in the same direction the whole time. So it goes down, 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 and then back up as I'm rotating the prism. So here they're matched up, and you can see that the glass one is bending the light more than this little one is the plastic one. So the little one is plastic, the big one is glass. And so they're bending, or they're changing that angle of the sunlight differently. And so I'm gonna rotate the plastic one. So here I'm rotating in the same direction. It goes down to its lowest and then it comes back up again. Same with the glass. I'm going to rotate in the same direction. It goes down and then comes back up. So you can see from that white reflection that I'm moving in the same direction the whole time. Same here. I'm moving in the same direction. That white reflection comes down, 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 but the spectrum goes down and then back up. And you can see at that point where the spectrum is at its lowest, you can be at a variety of angles and still be at that lowest. So that's an interesting thing for prisms. And it's even more interesting to make a rainbow with water droplets. And that's why a rainbow happens at those angles, is because when you're at that maximum deflection angle, well, a sphere, if you rotate a sphere, it stays like a sphere. But if you hit that drop in a whole region of points, you'll get that same maximum deflection angle. And that's why you can have a rainbow. It's because of this minimum that we're seeing with a triangle, which is different, but it's kind of the same idea. And so who knows what these colors are that we're seeing? Who knows what the colors are? Let me see some chat here. Do you know how to write a chat question? Zanzin obviously does. Red, blue, orange. Oh, yes. So we're seeing all these colors here, and it looks like the blue is, we call it refracted. The blue is moved the most. Oh, I should shut this door. The blue is moved the most, and the red is deflected the least. So what's happening is the prism is made out of something that can bend the light when the light hits it. but it's made out of something that bends the different colors slightly different amounts. And does anybody know what that is called? That bending of the light, different colors, different amounts? That's called dispersion. Refraction, Zanzin, is the word. Refraction is the bending, but that the different colors spread out, that's because of something called dispersion. So different colors get bent different amounts when they go through a substance. I have a bunch of questions that I want to get to, but I want people to know. Oh, did someone have his hand up? Ethan. Danielle, who is Ethan? Does Ethan have a question? No, you don't have a question. Okay. I thought there was a hand up, but that might have been a
There's
mistake.
a hand up. It's
Okay.
old friend, Roger.
Roger,
Can I ask a question?
please.
Okay, so my question is, we see the visible light is bent and there's different frequencies. If you go past the visible spectrum, is there any limit to frequency? It's not bent anymore?
That's an excellent question, Uncle Roger. Let's go right to that. Okay, this is an IR camera. And one thing about a lens, you probably know what a lens is. There's two things a lens has to do. Can you guess what those two things would be? Is anybody typing a message? A lens has to do two different things. One thing is light has to be able to get through it. If light can't get through a lens, that lens is no good. And the other thing the lens has to do is bend the light. So the light just can't go straight through it. It needs to get refracted, like Zanzin was telling us. So the lens has to be able to bend the light and it has to let the light through. So what my old friend Roger said is there any point where the light doesn't get bent anymore? And you might notice this lens here looks like a what? What does that look like to you? It looks like a mirror, exactly. It looks exactly like a mirror. So this would not be a good lens for us because visible light can't get through it. But what happens is as the light gets beyond red, further and further, bigger and bigger wavelength than red, the glass doesn't bend it as much anymore. So you need a new material. So this material here, this lens is made out of something called germanium. And germanium can bend light even if it's at a very long wavelength. And sometimes we need to use that. Another thing that's used is silicon. If you're working at, it's also not this big wavelengths. This is to look at heat, but you could have another one. Fiber optic communications are at about twice the wavelength that humans can see. And in those, they sometimes use silicon. And if you've ever seen a silicon wafer, a polished silicon wafer, for us, it looks like a mirror. But for the light that's at a wavelength we can't see, it looks like a lens. Things can go through it. Okay, I want to talk now about the difference between a lens and a window. So I have some windows and some lenses. So here's a lens, and you can see this one here, it's fatter in the middle, here's the middle, than it is at the edges. So the edge is skinnier than the outside, which, if you think about it, looks a lot like the edge of a prism. Sorry about this prism being all cut. Here, this side is skinnier, and maybe we could pretend this was the middle, and then we put another one on top of it. So we'd kind of pretend that this was a lens, and you can see it's fat in the middle and skinnier at the two edges. So a lens kind of works like two prisms. very roughly. It would work like two prisms glued together. So it's skinny at the top, fat in the middle, and then skinny at the bottom. Let's see if we can, well, and then this would be a window. Like here's a window, you can see right through it. Here's a window. So what would be the difference, do you think, between a window? Oh, here's a round window. It's not that it's round, because this is just a round window too. So what do you think is the difference between a lens and a window? We'd call this a very strong lens because it's quite fat in the middle. Are people typing? What's the difference between a lens and a window? Here's a very special lens. A window doesn't bulge in the middle. That's what I was hoping people would say. Lenses are curved. Excellent. And I'm sorry, but I was trying to trick you. Okay. Because one thing, a lot of the questions that I got were so good. People do a lot of great thinking. And one thinking was, has anyone ever seen safety glasses? I got my hands on a pair of safety glasses and I looked at these and you can see right through them, but they're curved. So this is made out of plastic. I guess they could be made out of glass. So the glass is curved, but these don't change the light at all. The light goes right through them. One way you can see that the light isn't going through is if I turn my head sideways. You can see here's my head, and then where my glasses are goes in, and there's my skin, and then it comes out again. So this is a good way, if you're maybe watching a movie or a TV show, and you want to see, does that actor really wear glasses or not? If the line just comes straight through, you can tell that they're just pretending, they're just playing a role. They don't really have glasses. And I'll show that with these. If I just put them on, and I turn my head from side to side, it's a continuous line where my skin is, and then my skin through the lenses, or whatever we call these, I guess lenses, and then down to my skin again. So these ones here, they're not focusing or defocusing the light at all. These ones here, you can see that it goes way in when you get to my real skin. And then I have some of my wife's reading glasses. Unfortunately, one of the lenses popped out, so I can only put one lens on, which is probably good because they probably don't fit me. But here, my eye would actually look bigger through the lens than it does through, this is just air on this side. So that's one way to see what a lens is. But the difference is, I guess it, very good, Miss Heather. I'm being a pain, yeah. So the difference isn't that one is flat and the other is curved. And we could even take a piece of plexiglass and curve this. So it has to be thicker, like I'm going through right here, has to be a different thickness than going through right here. So there has to be a change of thickness as you go through at one point to the next point, to the next point, to the next point. So here, just like on a prism, if I send light through here, it's going through a thin piece of glass. If I send it through here, it's going through a thicker. So you want that continuous change of distance from one side of the lens to the other. How did I have this? Okay, so that would be a lens. It's got to be thicker on one side than the other. And someone asked a question, why a lens turns an image upside down. So let me see if I can show that to you. So I'm going to see if I can put a picture on here. Oh, yes, very nice. So I have a picture on this piece of paper. I'll probably have to turn the camera to see it. There. Can you see? That's a picture of what's outside my window. So let me show outside the window. Here's the window. Oh, I guess that might be saturating the camera, but that's what the window looks like. And now we'll put it back on this piece of paper. So there it is, and you can see that it is upside down. So there is an image that's upside down. Can you see that it's upside down? Oh, I do need to show you something about this, though. I might have to go to this smaller, tighter focus lens. Okay, here, I'm getting two images. Here's the outside on this one. We have to show that here. But I wanted to show that I can move my finger across the real lens and it doesn't block out any part of the image. So I can move my finger. Let me see, can I hold this up somehow? I'm gonna try to put it right. No. I have to get my clipboard, unless I can put it up on this. Yeah. So I've got this big lens. I have a focused image on here. Focused image on there. And I'm gonna run my finger right across the lens, and I don't cut out any part of the image. So what this lens does, it takes light from everywhere. Light from everywhere hits all over this lens and goes to one point. So let's say light from right here in the real world, in the real object, hits everywhere on this lens. All of that light goes to that one point there. Okay, and what we can do today is draw an image of 3 of those rays of light, just 3 of them. But first, I want to get back to a question that, that my old friend Roger asked. And that question was about light that we can't see. We can only see a tiny amount, we call it the electromagnetic spectrum. We can only see a tiny amount of that. Oh, my other prism went out of the sunlight here. So we can only see a tiny amount of that. But I have a machine that can see more of it. And before that, I want to talk about something called a diffraction grating. So I think my sister Polly gave me these glasses one year, and I'm going to shine a laser through them, and we're going to see the diffraction pattern. So what this is, you can see through it, kind of. Can you see through it? Yeah, you can see through it, but it has a very regular pattern of bumps in this direction and in this direction. So it's like a very fine mesh. And that very fine mesh, light is going to diffract off of it. So we talked about bending light. That was called refraction. Now we're going to talk about something called diffraction. So I have some different lasers, and I'm going to shine it through it onto the wall, and we'll see what happens. So here's a blue laser. I'm going to shine this through, and it diffracts. It makes all those dots on the blanket. And if I turn this, the diffraction pattern rotates with it. Okay. And now here is I think it's a green laser. And this also makes dot. That brightest one, we'd call that the 0th order diffraction. And then the ones around it would be 1st order, and then the ones around that would be 2nd order. And then here's a red laser. And can you tell me something about how far the dots are spaced apart? Okay, that's red. And then here's blue or violet. Oh, yeah, these are closer together or further or the same? The blue, red go further out. Yeah, red was way further up. And here's some red and blue together. Okay, so I have a machine that's called a spectrometer. And this machine can go beyond what we can see. So I'm going to try to tilt the camera down onto this. So here's the computer screen of my spectrometer. So that's the computer screen. And now what I'm going to do is shine some lasers. It's a fiber, it's an optical fiber coupled. I'll just put this on my lap. So this is here's the spectrometer. It's made by a company called Ocean Optics. This is actually a piece of glass. You don't think you could bend a piece of glass. You wouldn't want to try to bend your window, but you can bend an optical fiber. An optical fiber is made out of fused silica, which is glass. So now what we're going to do, I'm hoping that this will work. Oh, we could just put this end of the fiber into the sunlight. So we saw a spectrum, we saw all those colors. Now let's see, oh, wow, yeah, we can certainly see this. So here is, but this is reversed. Because these would be the long, I'm pointing to the right. This is the long wavelength, this is the short wavelength. So it's reversed on my screen. I don't know if it is on yours. So that's what sunlight looks like. And you can see it's a big hill. There's a whole bunch of wavelengths on that. And that's what our eye sees as white light. So that's what we call that the solar spectrum. And as people said, we can't see here. We can't see here. Here's what we can see from the sun. And it's amazing that that's what our eyes can see. And that's what the sun puts out. So I've always been happy with that. And then we've got different lasers. This is a blue laser. Oh, this is a blue laser. And you can see it's just one line of light. So that's blue is the short wavelength. And then what else do we have? What does this say? I'm a little bit colorblind, so I have to read what this says. Well, we'll just shine it. Oh, this is the green one. Okay. Oh, and this is why I wanted to do this. Okay, because what do we have here? We don't just have one wavelength coming out of this. We have 3 wavelengths coming out of this. Okay, so there was one here, and one here. We can only see one of them. This is, where is it? This one here is the only one we can see. So these lasers are dangerous if you shine them through prisms. Because remember, the prism can bend that light. So it'll bend the green light, and then the other light that we can't see is still there, but it's not in line with the green light. So let me see where this other light would be. So there's this right here. This is light that's used to excite the laser medium. And then there's another wavelength. Let me see where that is. Way over here. So it's a little complicated. So if you don't understand this, that's fine. But here's what's happening. The light here is exciting electrons. They put out light here. So it's actually an infrared laser. And then they take 2 photons in the infrared and they do something called second harmonic generation. They take 2 infrared photons and make 1 green photon. So this little laser here, when I was in graduate school, this would have cost about $50,000. Because what it is, it's a neodymium YAG laser, and it's intracavity doubled. So it's a huge, there's a lot of technology in this. This has nonlinear optical frequency doubling crystal in it, and it has laser diodes to pump the neodymium YAG. So it's an engineering marvel. I can't believe you can buy 3 of these for $10 on Amazon. But when I was in graduate school, this would have cost about $50,000. So there's been a lot of technical advances. This one here, this blue one, you couldn't have bought one of these when I was in graduate school. There was a Nobel Prize recently with blue LEDs. So this was a huge a developmental push, and the guy won the Nobel Prize for it, for coming up with blue LEDs. Since we're talking about that, I want to show you a flashlight that I have. Well, we'll see several flashlights. Okay, so this here, this is an LED flashlight. And let's look at the light that comes out of an LED flashlight. So what do you see there? It's not one big hill that comes up and down. Yes, 2 peaks. So this is a white LED flashlight. It looks white. Our eyes see it as white, but what it really is, it's a blue LED with some fluorescent material on it. So the blue LED is that more peaky peak, that's the short wavelength. And then the broader one is the fluorescent material that's on it. And then our eyes can only see like the integration of all the wavelengths together. So our eyes see all those different colors as white. Let's look at it. This is a light bulb flashlight. So this one here, it's just a filament light bulb. And this one here is a nice smooth peak like the sun. Okay, so a regular, well, I call it regular. I guess LED is more regular than a filament bulb now. But here, this would be called black body radiation, or just heating something up. I also have a compact fluorescent light bulb. I want to show you that. So this is a compact fluorescent light bulb, and these have a very interesting spectrum. These are also very peaky. So it's a lot of discrete colors, but our eyes put those different colors together. Even though they're just discrete colors, our eyes see this as white light. This is really fun to look at with diffraction grading. So those glasses, maybe you have a pair of them or just a diffraction grating, you can see discrete images of the light bulb, and each one is a different color. So that's fun to look at with a diffraction grating. And then I have another one. This here is a UV light. I taught an optics camp. Oh, I think it was flickering on and off. I taught at an optics camp, and the high school teacher and I traded a few things. And I think she was going to throw this away. So I got this. And here, this is a UV light. And you can see, if I can get it to work, it's also very peaky. Now, one thing we can do is put a piece of plastic in front of it. Let's see if this plastic, it lets all the light through that we can see. But let's see what it can do to this. I think this one only cuts out that lowest wavelength one. Where did that go? This right here. Oh, is that too bright to see? This peak right here is the one that gets cut out by this see-through plastic, I think. I don't know if you can see it. Okay, maybe, I don't know if you're seeing that get cut out or not. So this, it can cut out the shortest wavelength. Oh yeah, I can see it now. So there's nothing here now when I'm going through the plastic. And now when the plastic's here, there's a little bit there. So we call this a long wavelength UV light. And the shortest of the long wavelengths are getting cut out by my piece of plexiglass. So if you buy UV sunglasses, just regular plastic would do the same thing probably. So you don't really have to pay extra for a piece of plastic to cut out UV light. Okay, how about you? Well, I won't do that class. Oh, have you seen chat from Polly? Oops. What did I do? Polly, where's your chat? Chat?
I wrote that you might be able to hold your diffraction lens over your computer camera and show us the compact bulb, and we might be able to see the different colored images.
Oh, wow. Yeah, we'll give it a try. The good thing about a video lecture is that you guys would not be hurt by the UV light because it won't go through this camera. So the weird thing is that this light bulb isn't working totally. Okay, so here's this camera I'm going to put in front of there, and you can see colors already. Maybe I should unplug this and fiddle with the light bulb. So this is the UV light. I don't know if you can see anything. Okay, there were some questions on why a lens flips things over. And I want to start with a spoon. If you take a spoon, this spoon is really polished. And there's two things we can do. Here, what are we seeing here? We're seeing, you can see an image in this spoon here. And it looks like, oh, that's the screen. That's the computer screen. It looks like it's upside down. So here's the bottom and there's the top. But if you take a spoon and you bring it right up to your eye, it's right side up again. So what I'm going to do, I have some magnifying mirrors, and let's look at some of those. So here's one. If I bring this in close, I'm seeing an image of the camera, and everything's right side up. There's Ellen, there's Polly, Joseph Fischer, there's Tristan and Caleb, and Danielle.
It's okay.
Okay, so if I'm in close, it's right side up. If I get further away, we get to this crazy period. And then if I go even further away, it's upside down. Oh, and that image of it is right side up again. Okay, so here, and I'm sure a lot of people have makeup mirrors in their family. And you've probably played with this, but it's an interesting thing, and we're about to show why this is happening.
We do have a comment that someone said our eyes flip things over because when images go into our eyes flip it so it is right side up.
Oh yes, very good. And we're going to do some drawings now of very special things about that kind of mirror and a lens. So I started out these drawings before we came on, and so here's one of those magnifying mirrors, and this is it's supposed to be a candle. So the candle is in very close, and this kind of mirror, what I wanted to talk about this mirror, the shape is called a parabola. Does anybody know what these are from? This shape, well, it would be a three-dimensional parabola. Flash bulbs for a camera, it could be a light. Yep. These are actually from flashlights. So like a 6-volt flashlight. Or cars have things like this too. So the special thing about a parabola is that there's a point in the parabola where if light starts at that point and hits the parabola, it's going to come out in a straight line. So if you have a flashlight, like this one here, this flashlight here, I can move it. So I don't know if you see things happening, but right now the light bulb is up, and now it's up again, down. So here it's down. So here the bulb is back in this parabola or paraboloid, and then if I turn it this way, now it's forward in this paraboloid. So these are really fun flashlights, and what we're doing, we're changing the location of that light. If we have the light right at the focus, if the light is right at the focus of this shiny paraboloid, all the light from that light bulb that hits the paraboloid will come out in a straight beam. So you can try this at night sometimes. If you don't have a flashlight like this, next time we see you, I'll bring you one. Or if you're from just a Warren County person, I'll come to the library one day, or some night would be better, and we'll try this. But what you can do is shine at something far away, and when the light bulb is right at the focus, you'll have the smallest beam you can get. So now we're going to draw something like that. So here's a candle, here's this focus, and a parabola isn't really part of a circle, but I'm pretending it's part of a circle. And if you don't go out far, like these ones went out pretty far, but if we just had this back part of it, it would be pretty close to part of a sphere. So a paraboloid, it flattens out here. It still goes out and forward forever, but you can tell that that's not part of a sphere, because this part here looks like it's almost straightening out. But here we have one that's just like that end of it. So you don't know if this is a sphere or a parabola. So this would be the center of the sphere. This would be the focus of the parabola. And now all the points, let's say we're just looking at the tip of this candle flame. Light from the tip of this candle flame could go up here, it could go here, it could go here. It could go anywhere except if it's blocked by the candle. So it could go in all directions. It could go forward too, right? But we're just going to look at 3 rays of light from that tippy tip of the candle. So I'll get a pen. So 1 ray of light, I'll get a different pen. 1 ray of light could seem like it's coming from that focus. So it would go up, and then it would go straight out. And then another one, if it goes straight into here, it's going to go through the focus. And now, has anyone ever ridden a bicycle? Okay, good. I see people nodding and saying yes. The thing about a bicycle, when a spoke hits the rim of the bicycle, what kind of angle is that? If here's the rim and a spoke comes down, it's going. Danielle, are you raising your hand? The spokes always come to the rim at a right angle. So if we're coming from the center, and we'll pretend this is the rim, it's going to bounce right back on itself. So these are 3 rays of light. Oh dear, wow. So here's 3 rays of light, and we want to see where they intersect, and they don't intersect. They're kind of diverging from each other. So what our eye does is follow these back. And then that's the very tippy tip of that flame. And down here, all 3 things happen together. If it goes straight in, it comes straight back. If it looks like it's going from here, it goes here. And if it goes from the focus, it goes straight back. So all those stay together. So the bottom of the candle stays here. And that was the top of the candle. So now here's what we get for our image of that. And that's what happens when you have one of these magnifying mirrors. You get it's a right side up image, and it's magnified. And that's exactly what we saw, right? We had a right side up image. Where is everybody? There. Oh, I'm too far away. That's why. So it's right side up, and it's bigger. So that's exactly what we're seeing there. Alan, are you right side up? Are you bigger? Well, you probably can't tell, but I can tell that you're bigger. So that's if we're inside the focus. If we're further away from the focus, we're going to be upside down and smaller. So let's try to draw those 3 rays again. Remember, light goes out in all directions. We're just going to look at 3 easy rays of light from the tip and see what they do. So if it goes through the center, it bounces back on itself. So let me draw that. So here, if it goes through the center, it bounces back on itself. If it goes straight in, it goes out through the focus. So here we have a ray of light going straight in, and that goes down through the focus. And then we have another one. If it goes through the focus, it goes straight out. And those are me kind of right here. So that's what that would be. Here's our object, and there's our image. So it's upside down, and it's probably a little smaller. And so that's also what we saw. It's upside down, and it's a little smaller. Okay, so those both worked. Are there other questions? I could do the same thing for lenses. Let me just do one for lenses. So here's a lens. A lens has a focal point. To find the focal point, you just hold the lens. If you put it in the sun is so far away. There's an equation for it. Here's the equation. I hope this is right side up for you. So 1 over the object, if the object is the sun close or far away? Far away. So it's in the bottom of the fraction. If you have a bag of M&Ms, is that a good thing? Yes. If you have to share them with a whole bunch of people, do you get more or less? Less. Let's say you have to share them with everybody in the country. Do you get more or less? Less. So the bigger the bottom of a fraction is, that's how many people you have to share it with. The sun is so far away that here you probably wouldn't even get a single M&M. So we can forget about this. Okay, the sun is so far away. This is how far away the object is. The object is the sun. We have such a big bottom, so we have to share it with so much that this fraction is tiny. So we could say 1 over the focal length is 1 over the image. So this means that where the focal point of this lens is where the image of it is. So if you have a lens and you focus the sunlight on it, that's the focal length of that lens. If your object is closer in, then it wouldn't be the focal point anymore. But that's a good way to do it. And it doesn't even have to be as far away as the sun. If you have a little lens, like this, it could just be the lights in your ceiling. That's plenty far enough away to just find the focal length. So again, let's do the same thing, and it's the same. If it goes through that focal point, so here's a ray of light that's going through the focal point, it'll come straight out. So any light that goes through the focal point will come straight out. Any light that goes through the center of the lens just keeps going. It doesn't get bent at all, right? That's like going through a prism. Up here, it's the same distance as here, because up here, this might be a little thicker, but that's a little thinner. Down here, this might be a little thinner, but that's a little thicker. So it's the same path if you go up or down a little bit from there. And then our other one, if we go straight in, it'll go through the focal point. So here we're going straight into the lens. It'll go through, I think I had this be my focal point. And then all three would meet right here. And again, the bottom, all three stay the same for that. So we'd have something like this. So we could maybe have a magnified image of our candle. Okay, so that's what I wanted to draw about that. I think I should go through the questions because I had some really great questions. Oh, and we're at a library, so I really enjoy. Ellen had some questions, and maybe some of you else will be able to ask more questions with this too. So we're at a library, so we need to show some respect for words. And one is the word lens. And I have some stuff here. Does anyone know what these are? You make soup out of these. Yes, these are lentils. And if you look at some of the early microscope, that's about how big their lenses are. And that's where the word lens comes from. It comes from lentil, because a lentil, you can imagine the first lenses, it was hard to make them and they'd never done it before. So they look just like, well, not the color, they were see-through, hopefully, but they were about this big and they were thicker in the middle than on the edges. So that's where the word lens comes from. And the lens, the first time it was used is the year 1673. So I thought, oh man, there was no word for lens until 1673. So you can imagine the Pilgrims came to America in what year? Well, way before 1673. Hopefully you know when they came to America. Okay, what about the word mirror? The word mirror, that meant to look at something and maybe look at something and be amazed. And that came from the 1200s, sometime in the 1200s is the first time they used the word mirror. And there's another word that sounds more like mirror, but it's kind of like a trick thing that can surprise you, maybe out in the desert. And that would be a mirage. And a mirage, the first time mirage was used was 1800. I thought that was neat. So here's the first question. I'm going to turn the lights on. So I was thinking about when lenses or mirrors were first used. Could the first mirror have been a still with no ripples puddle or lake? What do you think about that? What would be the first mirror that humans used? Maybe it was a puddle or a lake. I thought that was a great thought. And then I got some pictures. Here's a picture from the Middle Ages. And what we have here, does anybody know what this is? That's a dog with a nice hunk of meat. And then down here, if this is a dog with a hunk of meat, what do you think this could be? Are people about to answer? Are people typing? This is his reflection. Yes, very good, Zanzin. So does anyone know what this is from? A dog. Oh, that looks better than what I have. I'm going to get that one too. Do you remember that? But what's funny about this reflection? Yeah, it's Aesop's fable. Very good. Look at this. This is closest to the water. And then the reflection, it's furthest away. And that's not how reflections work. So then there was another one. This was from something called Kalila and Dimna. It's an Indian some drawing. They got this right. So here the tail is sticking up, and then in the reflection is going further away. So the closest things are closest in the reflection. The further away things are further in the reflection. So they got that right. Okay. So let me keep going. So that would be that. And then a lens. Did the sound stop? Oh no. Can you not hear me?
I think it was just me. Sorry.
Oh, okay, good. So I remember going to a museum and seeing some paintings by Dutch masters. And there was a little drop of water on one of the flowers or one of the stems. And in that drop was a magnified image. And the painter did such a great job. And this was hundreds of years ago. So I think little drops of water may have been magnifying glasses for a long time. Because with the surface tension, a drop of water is like a sphere. So maybe that's why. Oh, is it already 5 o'clock? I'm very sorry. Okay, here's a one. I just need to read this. Why does a mirror reverse your image left and right, and some telescopes flip the image upside down? So we just had upside down, right, with the lens and the mirror. But then listen to this. Since mirrors reverse images left and right, when you look in the rearview mirror of your car, why is the driver behind you in the left-hand car seat rather than on the right-hand side? So what's happening there? We have someone thinking. Okay, he's heard this story. Since mirrors reverse images, why would this happen? So he's using things that he knows to be true to question whether mirrors turn things. So here I've got a mirror, and how could this mirror, if I turn it this way, how does it know? Does it have a G-force thing on it? Does it have some inertial thing to know whether it's right side up or sideways? And the answer is that mirrors don't reverse things right and left. If you look at yourself in the mirror, I'm looking at myself in the mirror, and here's the left side, and in this picture, it's the left. I'm on the right. In the mirror, it's also on the right. So a mirror doesn't actually reverse images left and right. And you try this. I'm sure you all have bathroom mirrors. If you scratch your left ear, the ear on that side in the mirror is getting scratched. If I scratch my right ear, the ear on that side in the mirror is getting scratched. So what a mirror does is it doesn't reverse anything. But we're looking at that things the same way they are. It's almost we're looking through something. So if I write on this, so if I hold it up this way or hold it up this way, things get switched around. So here, one of these ways is going to be backwards. So what the mirror is doing when it comes back at you, I'm looking at things this way, and that's what the mirror sees, and it's not flipping them. It's keeping them the same, but we need it flipped. If I want that to make sense, I have to have it flip. So if I want to read it here, I need to flip it as I go to the other side. So that's what the mirror doesn't do. The mirror, it takes things that are close kind of stay close. Things that are far away are even far away in the mirror. So it kind of reverses things, but it's not going from left to right. And you could tell by here, how could it? How could it know? How could it know to keep up and down, but side to side, it would know how to flip that somehow. And you might think, oh, it's because I have two eyes. So if I close one eye, then it will flip. But that's not true either. Okay, that's what I wanted to show today. Oh, here's a corner cube. I didn't get to show this. A corner cube can, you'll go through two mirrors, so it's back to normal. There was another question. We did some with not being able to see the light. Okay, I think we should stop now because it's 5 o'clock. Thanks very much. I had a lot of other things, but oh, here's one thing I have to show. There was a question about how come see-through things, how can there be a reflection if it's see-through? And here I have a bunch of stuff in this cup, and I'll take some out. Here, I have these spheres and some blocks in here, but they're pretty much the same index of refraction as the water. So they're not bending the light at all when they're in the water. When I take them out, now air and this jello type stuff have different bending of air. So the air isn't getting bent when they're in the water. If the light travels the same speed in this ball is mostly water as it does in the water. So that's why we can't see it. It's they're transparent. Let me do it one more time. They're transparent because there's no difference. When you get to that interface, the light doesn't see it as an interface. Oh, let me show you one other thing. Oh, I dropped one. No, that's just the lens. So this here would be a big lens mount or a mirror mount. And I was trying to get that magnifying mirror to work. You need really fine adjustment. And then here's a little one. So this would be for a little mirror lens, and here's one for a big one. And this big one, 1, 2, 3, 4, 5, maybe it's five times the diameter, but you can put, it's 5 times more in this direction, but also in this direction. So it ends up being 25 times more light can go through this than this little one. Okay, I think I should stop there. There's always more stuff to talk about, but come visit and we'll do more. Okay, thanks a lot.